So Becca, Mark, and Mohammed worked alone for the first semester and a half, creating our website, coming up with our long-term goals and plans, finding our community partner WindAid, and creating an organization from the ground up. And then in November of 2022, they recruited their first new class of GAIA organizers. Those are some of the photos of the organizers that are still here today. So we have Anna, our chief marketing officer, Sophia, one of our marketing sub-team members. Up there in the corner is AJ, who you'll be hearing a presentation from later today. And then I'm also down there. And yeah, and then that was the mission statement that we created, which we like to often reiterate in our team meetings, that GAIA is a national competition that empowers college teams to conceive, design, prototype, and execute high-impact solutions for global sustainability. And at this point, I would be remiss if I didn't take a further look into our community partner, WindAid. The WindAid Institute is a nonprofit based in Trujillo, Peru. WindAid provides rural electrification to the countryside of Peru by building wind turbines from scratch. We chose to partner with WindAid not only for their superb work for the people of Peru, but their similar values to GAIA about the importance of providing students the opportunity to create hands-on impact. WindAid operates on a model of allowing students to come to their workshop to build these turbines and implement them in the community. They sponsor cohorts of students to come stay in Trujillo for 4 weeks while gaining technical, hands-on experience in their workshop and traveling to the rural community to see the impact they make on the lives of the local Peruvians. As with any new organization, the first year of GAIA had some bumps in the roads, but was highlighted by the successful work of our first team, the British University in Egypt. Although they did not field a team to compete this year, they did actively participate in our competition the first year of GAIA and allowed us to gain an understanding of how we wanted our second year as an organization to play out. In our first year as organizers, we figured out how we wanted GAIA to look both internally and externally. We learned how to work together, and our founders learned how to lead a team of 20 people working together to achieve one shared goal. This year, we recruited the majority of our team members with some notable faces like the head of our business team, Sunny, and the head of our international team, Kylie. We re-upped our partnership with WindAid for another incredible year of working together, and we worked on our long-term goals for GAIA and decided to focus on a rebuilding year. All the while, we were planning our first trip to Peru to visit our community partner, WindAid. These are some photos of our team this year. Yeah. And then over winter break this year, GAIA achieved our first major milestone, winning a 5K grant that allowed us to send 3 Cornellians, including one of our original founders, Mark, to Trujillo, Peru to do research for a problem statement, scope out the WindAid site, and build a turbine for our partner community. It was a really valuable trip for us because we were able to gain face-to-face connection with our community partner and meet the organizer of WindAid that we have been interfacing with for the past 2 years, Gandhi. And then this is like a photo from the site, and then that's them holding a GAIA banner down at the workshop. And now we have reached today. We're at our first scale in-person demo day. This has been a long time coming for us organizers, and we could not be more thrilled to be here today. Thank you to the GAIA organizers who made this possible, the ELP team of Miriam, Rob, and Erica, and of course, the competitors. We're so excited to hear about the solution you've created for this year's problem statement. That's it. Okay. I think yours, because you have the rest of the stuff, I would say. Mm. Did you use this one at all, or is it just this one? Okay.
Okay. Hello, I am Becca, and I am the technical lead of GAIA, as well as one of the original co-founders. And I'm going to share a brief presentation about the more technical side of GAIA. This will still not be a technical presentation, but it will be an overview of what the technical team does. So I'll be talking about the problem statement, which the technical team is responsible for writing, the trip to Peru that we recently executed in January, the generator modeling project, which the GAIA organizers technical team took on as part of our scope this year, and then also looking forwards towards the future of the technical side of GAIA. So GAIA was started with a mission of impact, and we were searching for a way to define impact in a way that can be measured and therefore used as engineering goals. And a great example that we drew from heavily of this is the United Nations Sustainable Development Goals. If you aren't familiar with them, these are 17 goals that were created in 2015 by the United Nations and are set with a goal completion date of 2030. And they include all of the goals that you see here. And for GAIA's first problem statement, we are focusing specifically on goal number 7, which is affordable and clean energy for all. And to achieve that goal, we have partnered with the Wind Aid Institute, a NGO or non-governmental organization based in Trujillo, Peru. And Wind Aid's goal is to create and install locally manufactured small wind turbines. And this is for the purpose of rural electrification for households who otherwise do not have any access to electricity. And specifically, Wind Aid has a design that they have been working with for years of their turbine. It's about 200 watts, enough to light a couple of light bulbs in the household. And the main challenge that they're facing is that this design is still expensive. And so we are working with them as GAIA to help innovate on the design to reduce the cost. And the design of the Wind Aid turbine is inspired heavily from a design by someone named Hugh Piggott from the United Kingdom, who has done a lot of work with locally manufactured small wind turbines all over, and especially in Latin America. And based on our discussions with Wind Aid, the biggest area of cost concern for them right now is their controller. The controller is a part that cannot be locally sourced from Peru, the only part of the turbine that is the case for. And so they currently import their controller from a company in China, and the controller itself costs $100, but there's an additional $200 of shipping and tariffs and import taxes on that. And that's like a pretty major part of the overall turbine cost. And so that is why the problem statement this year is focusing on how can we reduce the cost of the controller. And so diving into the problem statement, this is a document that the GAIA technical team creates each year to guide the competitors who are entering with engineering functional requirements, design requirements, optimization objectives, and a wealth of technical resources and information. And so we created the objectives working closely with Wind Aid about what would be most impactful for them. And so that is why the emphasis is more on cost reduction than it is on power improvement, because there is not going to be that much benefit to a small amount of power increase, whereas there would be a lot more benefit to cost reduction because it would enable Wind Aid to make more turbines and give more people access to electricity who do not have it. And the requirements are derived both from physical constraints regarding the governing laws of all the subsystems, as well as the operational constraints and the operating environment. The operating environment of Peru in an outdoors location and needing to survive for many years. And the requirements also specifies subsystem interfaces between the different components. And finally, the problem statement contains a compendium of resources intended to help teams get started, both introductory and complex and detailed technical modeling. And we also included a week-by-week timeline. And so this is a screenshot of the part of the design requirements portion of our problem statement. And so you can see that the electronic system was required because it was the main focus of wind aid for cost reduction, with optional subsystems of the blades and the generator, and several representative design and functional requirements. And additionally, this is the part of the technical resources spreadsheet that we compiled to have all the information in a centralized location, sorted by subsystem, and easily searchable to increase the access to information and hopefully enable even first-time teams who have never worked with wind turbines before to be able to get up to speed. And so this problem statement represents phase 1 of the entire GAIA program. But the GAIA program has 3 total phases. This first phase is the prototype phase. It's a design, prototype, and test phase running through the school year, basically from September, culminating in this event in April. And that phase is with the goal of innovating on the design, exploring, and testing the proof of concept. The second phase is the pilot phase, or the implementation phase. This happens in the summer, and you'll hear more about that later on for sure. This summer in August will be the implementation phase, where the entrants actually travel to Peru and implement their design. And the third phase of GAIA, which we have not yet realized yet with this inaugural cohort, but where we eventually hope to get to, is scale, where year after year, the engineers can iterate on their design with continuous improvement, do monitoring and maintenance work of the turbine, and most importantly, scale the solution to have a broader reach and ultimately to produce more impact, which is what GAIA is all about. And so I will next talk about some highlights from the trip to Peru that GAIA did a couple of months ago in January. This was a scoping trip to help gain information about the wind turbine and inform the problem statement. And so here's the picture again that you saw earlier of the GAIA team with Gandhi, who is the executive director of Wind Aid Institute. Some objectives of the January Peru trip are listed here. We are wanting to get data for both the wind aid generator and an alternate generator design that we call the Laplace generator, that another organization was working with Wind Aid to develop. Basically to get data for the 2 of them and compare them and determine the advantages and disadvantages of each. And then objectives 3 and 4 were about understanding the constraints that are relevant in Peru. And so the constraints related to the current manufacturing and maintenance process so that they can be improved with very specific recommendations in the problem statement, and also to understand supply chain, especially for electronics, as the electronics are the main pieces that could not be locally sourced for the wind aid turbine so far. And then 5th, understanding the context with the ultimate end users and understanding its role in the community for better user-centered design. And then finally, a reach goal was to also get data for the blades of the turbine. And so that was our schedule. And great, this is playing. So here is a video of the generator dynamometer system running. And so I'll point out each of these components. The green machine is an induction motor that we are powering from wall power and using to spin the white machine, which is the Laplace generator in this case. And this is called a dynamometer, and that's how we aimed to load the generator in order to collect data. And the Laplace generator would then be hooked up to the controller that we're also testing. And so, as I mentioned, another goal of this trip was to do some electronic supply chain scoping. Here's a picture from YMYS Electronics Store in Trujillo. This is one of the electronic stores that our team went to get an idea of their inventory, the kinds of components that were available and the kinds of components that were not available. And so this was really helpful to see that sort of like commodity components like these buttons and switches are quite available, but you won't necessarily be able to find something with a specific part number or very specific specifications, as well as understanding the sensors that are available. And so we detailed all of the findings from this January Peru trip in a report to give to WindAid, and that will serve as documentation for ourselves as well as other people who work with WindAid in the future. And so the accomplishments, as I mentioned, being able to better understand the supply chain, getting some valuable generator data, although we were not able to get all the generator data that we were hoping for. And so that would be a future plan. And you can hear more about that in the generator technical presentation, as well as we did not have the opportunity to gather blade data for the aerodynamics. All right, so I'll move on to generator modeling. This is another separate function that the technical team of the GAIA organizers works on. This was originally a portion of the problem statement for an additional team, but that team ended up not being able to participate this year. And so in order to try to still have the most positive impact that we can for WindAid, our technical team is also taking on this modeling project. And so the reason that we want to do modeling of the generator is that a previous master's thesis has done a pretty thorough analysis of the WindAid aerodynamics and the blades, finding that they are pretty near to optimal, and they can produce more than 500 watts of mechanical power. But on the other hand, the actual WindAid turbine is only producing a maximum of 240 watts of electrical power. And so that's less than half. And so you can see that the WindAid generator is quite unoptimized. It's not very efficient from a power perspective. And also it is rather expensive, costing more than $250. And so the objective would be to model the operation of the generator so that we can improve the power as well as the cost. And this will help, especially by reducing the cost, be able to bring WindAid turbines to more people in Peru. And so moving on to the next steps, another aspect of the technical team in the future will be to create a systems model. This will help to unify all the different subsystems and will be used in our problem statement in future years as the direct measure of impact. That basically, by including a physics model that has aerodynamics, the generator, the controller, and the battery, and the objective that we model is to minimize the number of hours in a year where the battery has run out of charge, and therefore the households do not have access to that electricity. That is a very a metric that aligns very well with the direct impact on people and their quality of life. And so this is why it's really important for us to make this systems model to be able to say how much an impact on an individual subsystem level will impact the overall goal of helping people have access to electricity who otherwise would not. All right, so we will get started with the next technical presentation. This one, as I mentioned before, was originally included in the scope of the problem statement for another competitive team, the MIT team, but they were not able to finish the project. And so the GAIA organizer team is completing this project, and we are excited to show you our model calculation and results for the WindAid generator. So I will walk through the goals of this project and additionally some more technical details about the Peru trip that happened in January, where we aimed to characterize the existing generators. Then I will talk through the existing solutions in detail, go through our design process, our modeling as well as design optimization process, and then end with some future work for the generator system. Starting off with the goals. So as we mentioned in the previous presentation, the current WindAid generator has an efficiency of less than 50%, and it uses a pretty large amount of both magnetic material and copper. And so we wanted to optimize the power efficiency, the economic efficiency, while maintaining the level of manufacturability with an emphasis on locally sourced components from Trujillo, Peru. And in particular, on the power efficiency side, we want to make sure that the generator can match the amount of torque that the aerodynamics or the blades are capable of producing. And on the economic side, that is reducing the amount of magnetic material, which is, apart from the controller, the magnets are the only other piece of the turbine that cannot be sourced from Trujillo. The magnets have to come from Lima currently, in addition to the copper, which is the biggest single cost component on the generator. So here's some more technical details about the dynamometer setup in the January Peru trip. So there is a AC power supply, a transformer, in fact, that we use to power a induction motor, that is the green device, and then these are mechanically coupled through the shaft to the generator. The Laplace generator is the one shown in the picture. And the Laplace generator is generating into a controller. That's an MPPT controller. The competitive team talked a little about this. It's a maximum power point tracking controller that basically ensures that the optimal tip speed ratio, which is an aerodynamic parameter, is maintained on the turbine. And so what we wanted to do with this dynamometer setup is basically by putting the motor and the generator together, you're able to load the generator. And so it's an alternative to spinning it with a drill, like we just saw the demonstration of, but being able to put a lot more power into it to see how it operates and basically obtain the entire torque speed curve and efficiency map, which means the efficiency as a function of torque and speed. And some secondary objectives that we had were to characterize the static parameters. That would be, for example, the resistance and inductance of the winding, as well as the back EMF constant. And those are all parameters that we input into the model, which are necessary for benchmarking and validation purposes. And so here are some measurements shown that we took on the pro trip. So we successfully were able to measure the back EMF constant by measuring the AC output voltage of the generator at various different rotational speeds to get a linear fit for the back EMF constant. And then separately, that second graph there shows a transient response of voltage over time on the winding. And this was in response to a step input, and the natural frequency and damping coefficient of this underdamped response allows us to characterize the winding impedance. So that is both the resistance and the imaginary component, the inductance of the winding. And so these were helpful pieces of data that we were able to measure on the Laplace generator in Peru that we can now use for benchmarking and validation. And unfortunately, some other measurements were not able to be accomplished on that trip. And so namely, the piece of data that we were most looking forward to gathering, the torque speed curve and efficiency map, we were not able to get. And one reason that initially prevented us from getting this was that the capacitor in the MPPT controller that we were using blew. And so initially we were unsure why this was happening, but we're able to trace it back to the back EMF constant of the Laplace generator being too high. And so what that means is that for a given rotational speed that is typical of something that the wind might spin the turbine at, the voltage that is produced on the generator is too high to a level that damages the controller. We measured more than 100 AC volts on the phase of the generator when the controller is designed to operate at a maximum of 48 volts. And so that resulted in a blown capacitor. And this is actually a really important learning point, because without this testing, we wouldn't have known that the back EMF constant of the Laplace generator was not suitable for the wind system. That basically it was not suitable to be used with a 12-volt battery system. And so that needs to be taken into account in the future when suggesting any design considerations that even though the Laplace generator theoretically could produce twice the power, because its voltage was mismatched, in reality, it was not able to be very effective, and it broke the controller. And so we did have a spare MPPT controller. So after the broken capacitor, we were able to use that spare one. And still with that spare one, because of the controller being different than the typical controller that Windade uses for their other turbines, we were unable to get that controller to actually absorb any power or operate at load. And it's still a little bit unclear why this was the case, but this prevented us from getting even torque speed data at low speed, which is all we could have done given the mismatch of the back EMF constant. And so these are measurements that, although we would have liked to have had, are things that we're still able to work around given our validation of the static parameters in the model. And so existing solutions, I mentioned briefly the Laplace generator, and I want to go a little bit more in depth on this generator and its assumptions, and as well as other existing models before diving into our own model. So the most obvious existing solution is the standard generator design that Windade has been using for years. And so this is based off of the Hugh Pigott turbine design. It is an axial flux machine that contains 8 magnets or 8 poles, and it is wound by hand, the copper coils, and the magnets are placed on a piece of steel. And here's a pie chart showing the cost breakdown of the current Windade generator based on a bill of materials that Windade has sent us. And you can see that the largest cost component is actually the copper, followed by an assortment of mechanical components like the shafts and the bearings and the screws, all those small things that add up, as well as the magnets being other really big cost components. And the steel plate behind the magnets is not a particularly large cost component. And additionally, there is a zinc plating on the magnets that is used to protect them from corrosion. So in some sense, you could lump that into the magnets, but it is broken out. And so knowing this cost breakdown is helpful because it lets us know where is most important to target for cost reductions. And so the mechanical cost reductions, it's not very feasible to have mechanical cost reductions because those are all components that need to exist, and none of those individual components are very expensive, and the amount of torque should not change very substantially because we still want to be able to handle the full aerodynamic torque. And so that's why we're focusing on the magnets and the copper as the 2 primary areas of cost reduction for the generator. And so to analyze this in like an optimization, we need an electromagnetic model of the underlying equations so that we can know if we change what aspect of the design, what will be the effect on the overall operating parameters. And so the starting point that we had for this electromagnetic model was a model created by a engineering senior design team at Dartmouth about 6 years ago. And so we call this the Dartmouth model. They had a model that includes finite element analysis using the FEM, or finite element magnetic method, package. And so it also includes the aerodynamics. Basically, they input a curve for the blades, CP versus lambda, that's coefficient of performance versus tip speed ratio, and combines that with a more detailed electromagnetic model. And they were able to validate this model by taking a couple of experimental data points with a passive rectifier in their shop. And so it's helpful as a baseline. However, there are many drawbacks to the Dartmouth model that as we looked more into it, we found. And so one that is kind of glaring to us was there was unfortunately a factor of 4 error in the power caused by swapping the diameter of the blades with the radius of the blades. And so this meant that right off the bat, none of the conclusions could really be trusted, although that is a very simple thing to fix in the model. And as we dug even further into it, basically finding that the torque versus speed curve used did not seem to really align with our expectations. And so part of that is they're assuming passive rectification only, so basically a diode rectifier, and they're not assuming a active controller. And this can change the torque speed curve. Until very recently, we were not aware of that distinction of the different shapes of torque speed curves depending on the type of rectification. And so we're learning more about that in this process of modeling, and we'll hopefully be able to better evaluate exactly how we need to tweak the Dartmouth model to take that into account. But we can see the graph here shows the ultimate torque versus speed curve that the Dartmouth model produced. And they are predicting a power of only 25 watts for the generator, as well as an efficiency of 89%. And so these numbers really aren't matching up with, we know that the current wind aid generator is able to produce 240 watts of electrical power, and that its efficiency is, in one measurement, was around 47%. And so it is both overestimating the efficiency and drastically underestimating the power, even once you account for this factor of 4 error from the diameter and radius. And so we determined that this model, while it was helpful as a baseline, needed definitely a lot of work and further investigation before we could use it to make decisions to suggest a wind aid. The second existing piece of work that we had to go off of for the generator was the Laplace generator. So Laplace Laboratories is, I believe, a national lab located in France, and they worked with wind aid to design a new generator, hoping to take into account the drawbacks of the standard wind aid design. And so their generator is pictured there. There's one 3D printed version in white, and then one manufactured using realistic locally sourced materials like steel, or sorry, not steel, that's a composite on the right. And so the benefits of the Laplace generator, they use larger, stronger magnets. And so in particular, the original wind aid design used N42 strength magnets, whereas the Laplace generator uses N52 strength neodymium magnets. So that's basically the strongest there is. And there's also a substantially reduced air gap, basically meaning that you can get the magnet and the coils a lot closer together. And that increases the magnetic field through the air gap, which is one of the most important operating parameters for the torque of the system. And so because of those design changes, the theoretical capability of the Laplace generator is it can handle more than twice the power of the wind aid generator. And this is useful because it would allow operation of the entire torque speed curve that is aerodynamically possible. So we would no longer be generator limited. However, the biggest drawback with the Laplace generator is something that we found on the January Peru trip, that the back EMF constant is way too high. And at typical wind speeds, it would be producing 70 volts and is incompatible with most commercially available controllers. And that's a pretty major problem that will prevent even like integration and testing of this device. And so we are hoping to have a little bit more insight and discussion with the Laplace team in the future about whether this was a calculation error on their part or a misunderstanding of requirements, or where this discrepancy might have come from. Another interesting fact about the Laplace generator is that it does not use steel. And this is rather strange. So as we saw like 2 slides ago, the cost of steel in the wind aid turbine right now is less than 5% of the total cost. Steel is not a particularly rare raw material in the context of Peru, but the Laplace report that we read basically said that the designers were wanting to minimize and eliminate the use of steel because according to them, it was a more scarce material. And we have also asked wind aid about this, and they were kind of like, well, we don't really have a problem with using steel. And so we think that this was perhaps a miscommunicated design requirement that means that the generator could actually benefit from using steel again. That would make it able to use smaller magnets, perhaps even less copper, and be cheaper while still achieving the same levels of magnetic flux, because the steel helps to prevent flux leakage leaking out of the generator. And because it uses primarily the bigger and more magnets, but also just overall construction-wise, the Laplace generator is 50% more expensive than the standard wind aid design. So it's in fact going in the wrong direction, although it does have more power. And so we were hoping to learn from the drawbacks of each of these previous design processes and these models to synthesize a recommended generator design that we could recommend to wind aid for the future. And so on the physics side, we looked at the coil, magnet, air gap, and steel. And so with the coil, on most standard motors in like machinery, they are wound using a machine. And that means that they're able to have a lot more flexibility in their winding design. However, because being locally manufactured is a really big priority for wind aid, their coils are wound by hand using like a machine with a crank on it. And so that places constraints on the dimensions, the number of turns, and the wire gauge that can reasonably be used in the coil. And the coil does not affect cost very much because the gauge of wire, it doesn't cost that much different between different gauges of wire, but it is a substantial contributor to cost, the overall amount of copper that is used. So in that sense, the coils do play an important role. And then on the air gap side, we already talked about minimizing air gap will increase the magnetic field through the air gap and therefore increase the torque of the machine. which leads to more power. However, on the flip side, having such a small air gap is a tolerance issue, which decreases the manufacturability. And so this is a constraint that requires a little bit more discussion and back and forth with Windade about what level of tolerance is realistic in their workshop and given their manufacturing techniques that we could go down to a smaller air gap. And then additionally, the magnet properties. So the big difference between the Windade generator and the Plus generator was the number, size, and strength of the magnets. And so our model accounts for all of these things. And then finally, the steel. We model steel in our electromagnetic model as an infinite permeability material, which is a little bit of an ideal assumption. But to mitigate the effect of this, we do limit the magnetic field through the steel to prevent saturation in it. And so with this physics-based simulation that we're able to build, we can test a whole bunch of different combinations, and ultimately we need some selection criteria. How are we going to decide from all the different possible generator designs which one we recommend? And so the criteria we ended up using is minimizing two different objectives, the mass of magnets and the mass of copper, because again, those were the two big cost contributors that are able to be changed by the design of the generator. And then a constraint of this process is that we need sufficient torque to basically allow as much torque as the aerodynamics as the blades are able to provide, up to a maximum wind speed of 10 meters per second, which is the largest typical wind speed in this part of Peru. And so given this selection criteria, we're able to incorporate the power efficiency with that constraint, basically enforcing the torque speed curve of the motor is always above what the blades can provide. And we use the coefficient of performance versus tip speed ratio curve. And that ensures that there's no power left on the table, so to speak. And then on the cost efficiency side, that's where the minimizing magnet and copper mass comes in. And by hopefully reducing the cost of the controller, it will allow Windade to produce more turbines. And of course, keeping the voltage low. We just basically include the DC voltage of 12 volts as a parameter in the optimization, so it's not even needed as a constraint. And finally, for manufacturability, we filter the designs based on achievable air gap and number of turns. And those are currently just estimates that can be refined once we have further discussions about the manufacturability with Windade. So now I'll talk about the exact physics details of the model. So we have both a radial flux model and an axial flux model. These are two different types of generators or motors. Both of them are permanent magnet synchronous machines, but the direction of the flux of the magnetic field differs basically whether it is radial or axial, as the names would suggest. So for our radial flux model, radial flux machines are much more typical, and the Laplace machine is a radial flux machine. And so for the radial flux machine, we use a magnetic circuit model. Here's a diagram of that magnetic circuit where the permanent magnets are modeled as current sources, and then the different materials are modeled as reluctances, which are resistances to the flow of magnetic flux. And yeah, basically all of this analysis came from a very useful textbook by Professor Hanselman. And because it is all analytical, this means that it's able to run really fast. There's no numerical computation or like nonlinear equation solving that is required. And we're able to maintain some level of nonlinearity by using Fourier analysis. This basically composes a waveform into the fundamental and its higher harmonics. And we can see the effect and how much the motor diverges from the ideal sinusoidal motor. And with the steel, we calculate the thickness required to prevent saturation. And so the steel thickness is not a design variable, it's a output. And I'll contrast this with the axial flux model. Windade's existing machine is an axial flux machine, and therefore the Dartmouth model already has implemented an axial flux model that uses FEA, finite element analysis. And this is a more complex form of analysis. It lets you get greater detail, but it takes longer time. And some more detail that it gives you a more detailed spatial resolution of the flux. You can see from this image, for example, how the flux paths go from magnet to magnet and then through the steel, and it also includes real material parameters. So we're not assuming infinite permeability of the steel for this. The steel has some finite permeability in its material parameters. And so the bare bones of the Dartmouth model, we're still able to use the way it sets up this finite element analysis in the FEM software. But the main things that we're modifying are after it computes this, what do you do with magnetic field to get the torque speed curve and the power? Those are the main things that we are changing. And so this is a piece, the systems model that I mentioned before is not created yet, but ultimately, instead of assuming that the generator needs to produce as much torque as aerodynamically possible. In the future, for example, it might make sense to have a co-optimization between the aerodynamics and the blade design and the generator design, or even just look at what would happen. Is it worthwhile to have a smaller generator that does not quite get the maximum aerodynamic torque, but still gets plenty? And so for this type of analysis, we would be integrating the systems model, which again consists of the physics model of all the different disciplines, as well as a battery charge model to ultimately give us the metric of how many hours per year the family who's using the wind turbine does not have access to electricity because their battery is dead. And so that will be an alternate objective in the future. And some detail on the systems model. Basically, we have interaction now between the torque and speed of the aerodynamics and the torque and speed of the generator. So the aerodynamic curves are shown in orange and pink there. Basically, this comes from the coefficient of performance versus lambda curve that gets scaled appropriately to find the aerodynamic torque and speed. And then the generator torque and speed capability is overlaid on that, and we can find what are the feasible operating regimes of these combined constraints. And given the overlap of these curves, we will change that. We'll transform that into a mechanical power as a function of wind speed curve that can then be used to look up based on the wind speed over time, hourly weather data, to get the average mechanical power, run that through the efficiency to get the average electrical power, and that will go through the battery model to charge our model battery and determine how many hours a year the battery is empty. And so here are some results of running this model. And so you can see that the rotor is shown in black and the stator is shown in red. The optimal generator that was output of this optimization right now contains 15 slots and 10 poles. It can produce 8 Newton meters peak. It has a top speed of around 1700 RPM and it weighs 4 kilograms. And you can also see the torque speed curve there. And to do further analysis on all the different generators that were tested, basically this optimization brute forced every possible combination of different generator designs of different magnet sizes and placements and number of coils and all that. And we can make a scatter plot of what's called a Pareto front to look at the two objectives that we care about minimizing, the magnet mass and the copper mass. And so the designs are marked in orange that have the best trade-off combination of these two. And one thing to note here is that there are very few of these orange points that are called non-dominated. And so it is worth doing some additional analysis later to double check that fully makes sense. Are we testing enough designs? Do we need to expand the range of the sweep, for example? And especially that the Pareto curve is rather steep, that these orange dots form a roughly vertical line, whereas you might expect there to be more of a gradual trade-off. And so that's the thing that we will be looking into in the future as well before we officially recommend this to WindAid. But it is pretty promising that we're able to do this type of analysis for the radial flux machine. And also, if we know the per kilogram cost of magnetic material and of copper, we can plug those in to get an overall singular cost minimizing generator. So basically picking from one of these orange points, which one makes sense based on the relative prices of magnets and copper. And so looking forward on this project, based on the current optimization results, to minimize the total active mass, which is the sum of the copper and the magnetic mass, the trends that we observed from this optimization are to minimize a whole bunch of dimensions, which you would honestly expect because you want the materials to be as small as possible. And so everything is as small as it can within the constraint of having enough torque. And also the current results are showing that there is actually no relationship with the wire gauge, which would mean that the winding can be chosen pretty freely. That would be convenient if it is actually the case, but I'm a little bit suspicious of that result. And so we'll be looking into that further because I would expect there to be a relationship with the wire gauge. And so additional thing that we will be doing for this project going forward is resolving some confusion that recently came up with what the torque speed curve looks like for different types of rectifiers. I was mentioning active versus passive. So the active converter is what you would very standardly see as the torque speed curve of a motor or generator, where there's pretty flat torque that is dominated by thermals, it's current limited, followed by at higher speeds a linear slope down that is voltage limited. And that's imposed because there is a fixed amount of voltage available from the converter.
So then right now, Nico is going to spin a drill that will spin the generator. And then we should see, once he spins it fast enough, there will be wattage output on this controller's monitor right here. So I'm going to press this button and it's going to show the wattage, which is basically the amount of power that's going to the battery. As you can see on the symbol here, it's from the generator going to the battery. So basically the battery is charging. Can you hold it on the other way? This way. Or this way?
Yep. Yeah.
Okay. And then you can also observe the voltage readings on here from the rectifier outputs. So I guess should we spin? Okay, I'm gonna set it. Okay, we're ready. Okay. You can see that there was a little bit of wattage output on this. So you can see let's spin it faster again. Yes. And you got 18 watts in this, and you can see that we're kind of staying within the separate range of 55 volts that we are still under the yeah, 42 watts right now. Okay. Yeah, that was okay. Yeah.
You want to get a picture actually with everyone standing in front of the demo? That would be nice. Of the mission by empowering college teams to go through the entire design process, conception, design, prototyping, and execution of these solutions for global sustainability. I'm really proud of the Cornell competitor team who has been able to get all the way here as the first GAIA team to really engage in a demo day and be able to have a solution to the problem statement is really exciting. And I hope that we're able to continue empowering this team and other teams to have the same sort of impact. And so going back to, Katie was mentioning this a little bit in the opening speech, but GAIA has been around for a little bit more than 2 years now. Me, along with Mark and Mohammed, co-founded it as part of the engineering leadership program in March 2022. Then that was our founding. A year later, we got our funding through winning the Uni and Maxine Powell Social Impact Award through the Engineering Innovation Competition. And that was a big step forward to enable us to start actually planning the trips. And then our successes in January of our first travel to Wind Aid in Peru for the scoping trip, enabled by a $5,000 grant from the Einhorn Center. And then today, marking a big milestone as our first demo day. And overall, I'll go back here, through all of this, we have seen that it is really possible to take the needs of our NGO partner Wind Aid, translate them into design requirements through the problem statement, and then work with students iteratively to figure out the best solution and end up with models and, of course, a working prototype, which is really exciting. And so thank you to everyone for accomplishing that work. Next, I'll talk about the summer plans. So as we had mentioned, the plan is to implement the system in phase 2 of the GAIA program in the month of August in the Wind Aid workshop in Trujillo, Peru. But leading up to that, there are definitely some more things to do on both the technical and the operational side. And so our internal technology team, as well as we're continuing to work with the Cornell competitive team to finalize the system and be clear on exactly what the technical, the bill of materials, the technical scope, the plan of events for the trip, as well as figuring out the operations for that trip with our operations team. And so that will be ongoing through the next couple of weeks for organization and ultimately leading up to the trip in August. And an expected trip itinerary, which we can go more into detail about, and especially as we talk more with Gandhi and the other person who runs the hands-on part of the workshop at Wind Aid is Senora Bell, working with them. Our trip itinerary consists of finalizing the local sourcing of the rectifier and controller, assembling the system and testing it on the bench with those real locally sourced parts to verify that they are working, installing the controller on a turbine for data collection purposes in the workshop in Trujillo, and that will serve to test a lot of the edge cases and failure cases that might only occur when the system is on a real wind turbine as opposed to on the bench. And then finally, getting it out into the field pending Wind Aid's other installation dates, and that would be really concretizing the impact of having this new and cheaper controller system that a family can really be using for their electricity needs. And then our plans for next year. So we will be updating the problem statement based on all that we learned from this year. So this year, the projects that were executed was the controller getting all the way to the prototype stage and the generator only in the modeling stage. And this year used qualitative metrics in the problem statement. Next year, we're hoping that by continuing to work with Wind Aid, we'll be able to refine this even more to enable the co-design of different subsystems, including, for example, the controller, generator, energy storage like battery, and the blades. And then finally leveraging the system model that we've been planning to have the problem statement be really based around quantitative metrics so that design decisions can be made in a more logical and goal-oriented way is the goal for next year. A second goal for next year is to validate GAIA's operational model. And so I'll talk about 3 different aspects of GAIA's operational model and where we are on that. So as you know, GAIA is a relatively new a new organization. And one of the first hypotheses that we posited with defining GAIA was that college engineering students are a source of untapped potential for making impact. Hypothesizing that college students being eager to gain experience are willing to devote more time and energy than, for example, working engineers who would volunteer after hours, that colleges are a great place to have this sort of impact because colleges offer the monetary resources for prototyping and travel to help students do that, as well as technical guidance of mentors and professors, as even just peers and classmates. And finally, the existence of a gap in this operational model, a gap in this paradigm of impact for college engineers. Most existing engineering programs either focus on really rigorous engineering or having the global sustainability context, and there are pretty limited opportunities to do both. And that's what GAIA is really aiming to be, that intersection of having the rigorous engineering applied in this global sustainability context and using that to make the most impact possible. And so I think so far we have not observed any evidence that would negate this hypothesis, and it's still a thing that we will be refining in the coming year. The second piece of GAIA's operational model that we can validate next year once we finally have this first demo day under our belt is the structure of how GAIA works. And so we hypothesized that the best way to activate the untapped potential of college engineers for impact is to organize a yearly competition. Our motivation for this hypothesis is that students are really motivated by either competing or by learning. Those motivated by competing, it's kind of obvious that having competition will motivate them. Those motivated by learning will still be motivated by this competition because the best way to learn how to do something is to do it. And so by having this really hands-on impact-focused competition, that is the best way to learn how to have impact, is to really have impact and not to just think about how you would have impact. And that yearly competitions are a pretty proven structure that, especially at Cornell, the engineering project team ecosystem, but also at other universities, that will unify, energize, and focus engineering students towards this common goal. And one question that we have for this operational model that we'll be thinking about going into the future is avoiding the perceived conflict of interest related to, so us organizers are all Cornell students, and having competitors coming from different schools, including Cornell. And if we are to expand to multiple schools in the future, making sure that we're being very clear and fair about like the way that we're interacting with all the different teams and being able to help everyone as much as possible. And so we've previously done this with like some site visits to the MIT team earlier this year. And so we'll have to explore what that looks like as GAIA's scope grows and whether that is feasible or if there are other operational ways to do this. And a third piece of GAIA's operational model that we will be hoping to validate in the upcoming year is that our more like detailed way of operating that we hypothesize that new teams can successfully make progress on the problem statement when provided with technical resources, a suggested timeline, and weekly office hours. This hypothesis has been the one that we have struggled with, I think, the most out of the three as an organization. And so, as you're probably aware, we no longer have the MIT team competing with us. There were also other teams who were interested at the very beginning who never really started on the project. And so we are really hoping to, now that we have like a competitive team who has really gotten through it, to talk more with you guys about like how the experience was for you and how it can be made better in the future. And looking at providing more support in addition to the technical side on like the leadership and operations side, or whether we want to prioritize making sure that competitor teams have an experienced engineer on the team who is able to guide on the technical side, different things like that, or even exploring mature organizational structures that would not require building an organization from scratch, for example, senior design projects or existing project teams, all things which GAIA as the organizers will be considering. And we are eager to make these operations as good as they can be for the success of teams and ultimately to be able to enable the most amount of impact. And then an additional plan for the coming year would be to potentially expand to other competitors. And so these are some schools who have previously showed interest in GAIA or schools that we have potential connections to. And so we'll be deciding over the summer the exact scope of how many competitive teams we are aiming to have for the next year, trying to balance the amount of impact that can be had with breadth, with also the depth of amount of support that we're able to give each team. And then I'll move on to a more long-term vision for GAIA. So ultimately, we envision for GAIA to really become big for maybe not in 5 years, but in 10, 15 years to be, in every engineering college and to have like the same way that mature project teams like those from the Society of Automotive Engineers, like Formula and Baja are, for there to be many teams, mature teams, helping teams to be more independent and leveraging their own forms of funding and organization so that we can really have and like empower as much impact as possible. And on the partnership side, we hope to continue maintaining a long-term relationship with Windade, who has, as our first partner, been like great to work with. And then also in the longer-term timescale, adding on new partners who work on other sustainable development goals. As you remember, so far we're only addressing sustainable development goal number 7, and there are 17, so 16 more for us to explore. And so as we continue to grow in the future, it will be important to strategically look at all aspects of global sustainability and not just wind power. And I will finally conclude that the future is in our hands, that we are all here in this room because we care about impact and we care about achieving GAIA's mission. And I hope that this demo day has served to inspire and excite and empower all of you to be able to make an impact through GAIA and through any other endeavors that you do. And so I'll wrap up by giving a very warm thank you to all of the different organizations who helped us get to this point. Our community partner, the Windade Institute, the Cornell Engineering Leadership Program, who we were founded out of and who has continued to provide us organizational and leadership support, the Einhorn Center and the Engineering Innovation Competition, who have funded GAIA, the Engineering Project Teams Office, who helped make the trip to Peru in January possible, the Cornell Maker Club, who we have used the facilities and materials of for the testing of the prototype. And then finally, the C Lab, which is my lab, who we have leveraged the generator model of, which is also like my generator model, and who we have borrowed an N8 socket adapter from. And so thank you to everyone to all of these organizations, and GAIA would not be where we are without all of these organizations. And thank you.